Now that we have completed this module, let us review the key concepts that we have studied as part of this module. LTE proposes significant changes in the three major areas: the air interface, the radio network, and the core network. Key air interface changes include the introduction of orthogonal frequency division multiplexing (OFDM) technology, along with the fully integrated use of multiple antenna techniques such as multiple input multiple output (MIMO). As a result of these changes, LTE air interface can support very high data rates. LTE changes the hierarchical architecture of UMTS and converts the radio network into IP-based distributed network. IP-based backhaul will reduce the backhaul cost. A fully IP-based core network will replace the separate circuit switched and packet-based core network, which provides scalability and reduce cost. The new services can be introduced easily via the IP Multimedia Subsystem (IMS). The LTE network architecture, like any other mobile network, consists of three key components: user equipment called UE, access network, which in LTE is called Evolved UMTS Terrestrial Radio Access Network (ETRAN), packet core network, Evolved Packet Core (EPC). They work together to provide connectivity, mobility, and services for mobiles. At a high level, the network is comprised of a core network, EPC, and the access network, ETRAN. While the core network consists of many logical nodes, the access network is made up of essentially just one node, the evolved node B, eNode B, which connects to the UEs. The term LTE encompasses the evolution of the Universal Mobile Telecommunications System, UMTS, radio access through the evolved UTRAN, ETRAN. It is accompanied by an evolution of the non-radio aspects under the term System Architecture Evolution, SAE, which includes the Evolved Packet Core, EPC, network. Together, LTE and SAE comprise the Evolved Packet System, EPS. The EPC is responsible for the overall control of the UE and establishment of the bearers. Unlike 3G network architectures, LTE is significantly different, as it has no circuit core network for voice services. Voice services are established using an IP Multimedia Subsystem, also called IMS, environment beyond the EPC. There are several functions provided by the EPC, which include management of mobiles within its domain, authentication of subscribers, and establishment of the bearer paths to transport service traffic between the UE and a packet data network, PDN. The policy control and charging rules function is responsible for policy control decision-making. The HSS is defined as the subscriber database for the LTE EPC, while the MME manages subscribers while they are in the network. The SGW and PGW are used explicitly for routing user traffic. The PGW is the mobile's IP address anchor, and the gateway between a PDN and the LTE EPC. The SGW, in addition to being a router, is the local mobility anchor, so as a UE moves from one eNode B to another, the bearer traffic will get switched at the SGW. The LTE air interface, referred to in LTE standards as the LTE-U interface, handles all signaling between the UE and the network. It carries all signaling messages between the ENB and the MME, as well as all user traffic between the ENB and the SGW. Both the control plane and user plane of the UE interface are supported by the same set of interface functions like security and header compression, and are all carried by the physical layer over the air. The physical layer in LTE is based upon orthogonal frequency division multiplexing, OFDM, using orthogonal frequency division multiple access, OFDMA, in the downlink, and a variant of this called single carrier frequency division multiple access, SCFDMA, in the uplink. There are several functions which support signaling and traffic on the air interface. These include security, like message authentication and encryption, IP header compression, data protection with encoding and retransmission, UE synchronization with the LTE physical layer, broadcast of system information. The signaling carried on this interface will support functions like connection management, handover and paging. We have discussed protocol stack over various interfaces. In summary, the protocol stack over the user plane is shown in the diagram. The user plane protocol stack between the eNode B and UE consists of the following sublayers: PDCP, Packet Data Convergence Protocol, RLC, Radio Link Control, and Medium Access Control, MAC. An IP packet for a UE is encapsulated in an EPC-specific protocol and channeled between the PGW and the eNode B for transmission to the UE. Different tunneling protocols are used across different interfaces. A 3GPP-specific tunneling protocol called the GPRS Tunneling Protocol, GTP, is used on S1 interface between the eNode B and SGW and on the S5 per second 8 interface between the SGW and PGW. Please click on the next to proceed further. The protocol stack over the control plane is shown on your screen. The lower layers perform the same functions as for the user plane with the exception that there is no header compression function for the control plane. The Radio Resource Controller RRC protocol is known as Layer 3 in the AS protocol stack. It is the main controlling function in the AS, being responsible for establishing the radio bearers and configuring all the lower layers using RRC signaling between the eNode B and the UE. X2AP and S1AP are the control plane protocol over X2C and S1MME interfaces respectively. In EPS, non-access stratum procedures include the procedures used by the protocols for mobility management and session management between user equipment and MME. Please click on the next to proceed further. Now, let us look into OFDMA, orthogonal frequency division multiple access. For the downlink 3GPP chose OFDMA for LTE, which incorporates elements of time division multiple access, TDMA. OFDMA allows subsets of the subcarriers to be allocated dynamically among the different users on the channel. OFDMA allows multiple users to access subcarriers simultaneously. In this example, 3 users share multiple subcarriers. The assignment of subcarriers for a user can be changed at every symbol time. OFDMA results in a more robust system with increased capacity. On the uplink, The physical layer in LTE is based upon variant of OFDMA called Single Carrier Frequency Division Multiple Access or SCFDMA. SCFDMA is a new single carrier multiple access technique which has similar structure and performance to OFDMA. A salient advantage of SCFDMA over OFDM is low to peak to average power ratio, PAPR, thus increasing battery life. The frame structure defines the frame, slot, and symbol in the time domain. All transmissions, in either direction, are organized into 10 milliseconds frames. Frames help the UE determine when certain events will occur, such as system broadcast messages. For example, a new master information block, MIB, is sent every 4 frames. Frames are subdivided into 10 subframes, SFs, each 1 millisecond long. System resources are allocated on a subframe basis. Similarly, each subframe contains 2 slots, each being 0.5 milliseconds long. So, in a 10 milliseconds frame, there are 10 1 millisecond subframes and 20 0.5 millisecond slots. A slot is made up of either 6 or 7 OFDM symbols, depending upon the cyclic prefix for the cell. There are 5 channels defined for the downlink, and 3 for uplink. LTE doesn't have the dedicated channels, which is a characteristic of packet-only systems such as UMTS. Before a UE can read any of the downlink channels, it must be synchronized to the downlink slot timing and frame structure. Synchronization signals are used by the UE to synchronize with the slot timing and to align to the framing in the downlink. Reference signals are always transmitted at a constant per RE power, and can be used by the UE to take measurements of the downlink of a cell. Let us discuss life of a UE. As the UE is power on, it looks for the LTE network, registers with the selected network and exchanges data with the network. Step 1. When the UE is powered on, it uses programmed information, or most recently used network information, to decide which frequency to use to start looking for an LTE network. After tuning its receiver to that frequency, UE searches for the LTE cell transmission on that frequency. Step 2. Once the UE finds LTE cell transmission, it starts listening to system information, which is broadcasted in that cell. During this time, the UE is in idle mode, where it just listens to the system. Step 3. After UE learns the LTE system information, it uses its system access parameters. UE tries to access the network, using random access channel. Since multiple UEs may try to access the network at the same time, using same uplink resources, collisions may occur. So access procedures are defined, to minimize, and resolve collisions. Step 4. UE now registers its presence with the network. The network authenticates the UE, and allocates an IP address. Finally, the network may allocate radio resources to the UE, to enable efficient user traffic exchange. In LTE, attaches the registration procedure that is followed. Once the UE sends an attach request, the eNode B will select MME to serve the mobile, and the initial attach request will be sent to the MME. In LTE, the MME will manage authentication between the HSS and the SIM card in the UE. After authentication passes, security will be established for NAS signaling, RRC signaling, and user traffic. Once attached at the MME will begin processing the PDN connectivity request from the UE. A bearer path is established between UE and the PGW. This bearer, referred to as a default bearer, will remain established until the UE is detached and provides always-on connectivity for the UE to the selected PDN. It is during the establishment of the default bearer that the PGW can assign an IP address for the UE. In LTE, a UE could be in one of the two mobility states, idle and active. A UE is said to be in the idle mode when the UE is not actively exchanging traffic. A UE is said to be in active mode when it is actively exchanging traffic. When UE is in idle mode, it executes one of the three mobility-related procedures: cell selection, cell reselection, and tracking area update. In the active mode, LTE needs to support two handover possibilities. One is the case where a UE moves from one cell to another cell with no change in MME, that is, intra-MME mobility. The second case is when a UE moves to a cell that requires a change in MME, that is, inter-MME mobility. We have walked through the evolutionary path of a wireless network, starting from GSM GPRS Edge, and evolving to UMTS, and onto LTE. Here we have seen how an LTE network may evolve directly from a GPRS network. Alternatively, LTE may evolve from a UMTS network, supporting HSPA, HSUPA and HSDPA, or from a UMTS network that has already evolved all the way to HSPA+. The maximum theoretical data rates are shown at each technology level. To summarize, requirement for LTE is to develop a framework for the evolution of the 3GPP radio access technology towards a high performance, improve cost efficiency and greater spectrum efficiency. LTE architecture consists of three key components: user equipment called UE, access network which in LTE is called Evolved UMTS Terrestrial Radio Access Network, ETRAN, and the Packet Core Network, Evolved Packet Core, EPC. In LTE, the circuit core network is eliminated and all voice calls in the LTE network will be handled as packet data services or voice over IP, VoIP. The access network, or EUTRAN, consists of only ENB. These ENB can collaborate with each other over a newly defined X2 interface for handover and radio resource management. Additionally, LTE is a non-hierarchical or flat architecture, meaning that the ENB exists in a many-to-many relationship with nodes in the EPC. The EPC's primary functions exist in the MME for managing mobiles, the SGW and PGW for traffic or bearer path, and the HSS as a subscription database.